Alright, in this tutorial we're going to continue on with the discussion of converting mass into energy by looking at two very important processes, fusion and fission. The former is hopefully a technology we can develop in the next few decades that will solve some of our energy crises, especially associated with electrical production. And fission is a process we've been doing for 4 or 5 decades now, mostly for peaceful purposes. Unfortunately, we dropped a few devices that take advantage of fission for destructive purposes. Fission and fusion are opposite reactions. One is to combine light things to make the heavier nuclei, and the other is the reverse. Take heavy nuclei and split them into lighter nuclei. So let's take fusion, which I believe is a little easier to understand conceptually. So it's a combining of light combining of light nuclei to form heavier nuclei, and why we're interested in this, it gives us extra energy. Okay, so we'll talk much more about fusion reactors later on next semester. The classic fusion reaction actually doesn't involve very simple hydrogen atoms. It involves isotopes of hydrogen, deuterium and tritium, which are given a symbol capital D and capital T, to fuse to form a helium or an alpha particle and a neutron, as designated above, and extra kinetic energy. Okay, and this kinetic energy does not come from any potential energy between these two nuclei. It comes from a mass transformation into making a more stable nucleus. If you recall the activity it did with the binding energy per nucleon, you will see that an alpha particle, He4, is much higher up on the curve than either of these, because this is more energetically desirable. It has a lower energy state than either of those two, and that's what nature prefers. Okay, so what it does is that when it combines, it will shed that extra energy in the form of kinetic energy of a neutron, and we can utilize that for some wonderful things. Okay, so let's break this down a little bit more. So there is the nuclear formula. D plus T gives us a helium nucleus plus a neutron and some kinetic energy. And the kinetic energy really is not a new particle. It's not some other particle. It's really from these two guys, but we'll talk more about that. I want you to recognize what a fusion reaction looks like. It's two light things. The D and the T don't give that away, but normally we would give the masses, and we get one product and maybe some particles that come out of it. So to get the idea of how much energy we get from this reaction, we want to calculate the mass defect. In other words, how much mass was, if you will, lost in forming this more stable nucleus. And of course, mass defect is the mass of the reactants minus the mass of the products. Actually, it's the other way around if we're being careful. So I'm going to probably get these reversed, but that's all right. So let's do this. This would be 4.0026. I'm sorry, I'm jumping ahead of myself. So we can fill in this table the mass of each one. You're not expected to know this. So 2.04. So the deuterium is roughly 2. The tritium is roughly 3. Helium nucleus we know is 4, but it's not exactly 4. And a neutron we know is a mass of 1. Or very close to it. Okay, so if we do the mass defect, I'm going to do the products. So there's my He. Now I'm going to put in add that to the neutron, because that also comes out of the reaction. And then I'm going to subtract from that the sum of my reactants. Okay. Now we can do the maths. I'll do that for you. On this side, the left side, is 5.0112 U minus 5.0311 U, and if we do the subtraction, we get negative 0.0189 atomic mass units. So negative meaning we lost mass. So it's not a whole lot of it. And we got to recall, if I want the energy equivalent, we know that a loss in mass of 1 U is equal to 931 MeV of energy. I don't need to do E equals mc squared again, because that's built in. And that translates to 17.6 MeV of energy for every time we fuse a deuterium and tritium nucleus. You do that for a mole of those, and you get quite a bit of energy. But that's, again, something we'll discuss another time. Now we can ask the question, talk about how this energy is distributed. The 17.6 is both for the helium nucleus and the neutron. So we can look at how that energy is partitioned between those two. And if we use a law of conservation of momentum, it becomes readily apparent. So we know that momentum has to be conserved. That if the overall momentum of the d and the t was 0, then we expect the helium nucleus and the neutron to move with an overall momentum of 0. So their momenta are pretty much the same. But since the neutron has 1/4 the mass roughly, and they have the same momentum, it would make sense that it has 4 times the velocity. And if it has 4 times the velocity, it turns out it has 4 times the kinetic energy. Now you might be thinking, wait, doesn't kinetic energy 1/2 mv squared, 4 squared is 16, but remember it has 1/4 of the mass, so that's where the 4 times comes from. So the neutron is what carries away most of the extra energy. And it's because it carries away the most of the extra energy, we can use it as a primary source of the heat exchange that occurs in a hypothetical fusion reactor. Actually, we do have fusion reactors at work, and this is where we would create the energy needed to create steam, to create electricity, but I get ahead of myself. Okay, I want you to try, you can do it right now, or you can do it later, is do a similar problem where we combine deuterium and deuterium to make a H3 nucleus plus a neutron. And what we want to do is compare its output in Ke compared to the DT one and see if it's more desirable. The second process we want to look at is the more mature technology, and that's fission. Okay, fission, to fission something is to split it in half, so it's generally with a very heavy nucleus, and it's split into what we call daughter nuclei. It's a simple way of saying lighter nuclei, and what we really care about it for, whether it's for peaceful purposes or for kabooms, it is the energetic neutrons. Now, we don't want to confuse fission with a nuclear decay, or radioactive decay. This is not something that happens spontaneously. You have to really be careful, EOUS, go out of your way to make fission occur. There has been one recorded instance in somewhere in Africa where some natural phenomenon was shown to be a fission process, but it's very, very rare. The reason that it's not something spontaneous is you have to take that heavy nucleus and you got to tweak it, and you tweak it with a neutron, an incoming neutron of just the right speed or energy. Okay, so the hallmark of a fission reaction is you got some nucleus that's pretty heavy, but you also have, as part of the reaction, a neutron. So when a neutron meets the X, you get lighter nuclei, Y and Z, plus 3 other neutrons. And this diagram here does a nice job. And in fact, it gives us an intermediate state. So we have neutron plus the, in this case, uranium nucleus. The neutron sticks and makes an isotope for a very, very short period of time. And then this would be, if you will, the arrow is the unstable nucleus. And then we get 1, 2 daughter nuclei, in this case krypton and barium, and then those 3 neutrons. Okay, so we're interested, again, like the fusion, is how much energy do we get for that fission. I'm sorry, Y and Z are daughter nuclei. So let me fill that in. Okay, so let's finish up with a quick little problem, very similar to the one before. So what do we know about it? The mass of the daughter products, which would be the Y and a Z plus the neutrons, is always going to be less than the mass of the nucleus plus neutron. All right, this lost mass goes into extra energy, kinetic energy, primarily, you can probably guess, in the neutrons. It doesn't really go into the daughter nuclei because they're so massive, so their momentum is carried more by their mass than their velocity. Therefore, they're not going to get a whole lot of kinetic energy. All right, so in order to do this, here is the breakdown. We have U2, there's a typical example, fissionable uranium plus a neutron gives us xenon, strontium, and 12 neutrons. And we got to make sure we're careful about that. I give the mass of each of the players here. Now we can calculate mass defect, so why don't I do that for you? This is a big, long pain in the butt one, so I got 135.9072 for the xenon minus 87.9056 for the strontium, is it? Yep. Minus, now I got to take and count the neutrons, but I have 12 of them, so I'm going to have minus 12 times 1.0086. Put brackets around that. Why was a big long one? Minus now the products, or excuse me, the reactants. So that's going to be 235.0439 plus the 1 neutron. Okay, that's a lot of accounting. I'll do the maths for you. This mass defect is negative 0.1365U. That's quite a bit, and that translates to an extra energy of 127 MeV. Okay, if I multiply this number by 931. So we can see we get a pretty decent amount of energy. Now that 127 MeV is distributed amongst those 12 neutrons. So if I divide this by 12, I get approximately 10 MeV per neutron. So it's not quite as power packing as, let's say, a fusion reaction in terms of energy per neutron. All right, and there is a problem on the back. It's not quite a fission problem. It is actually a decay, but that's all right. It's the same idea. So give that a try. We'll talk about it in class. And that will conclude our discussion of various processes in which we get matter turning into energy to, in this case, this is more exothermic rather than, like I'd say, almost like an endothermic type of mass defect from binding energy.